In this podcast, we will build on the concepts you learned in the Study Designs podcast and introduce some basic ways to measure the association between a potential cause and an effect. By the end of this podcast, you should understand the difference between a measure of disease occurrence and a measure of effect, how to calculate several measures of disease occurrence, the risk, the odds, and the incidence rate, how to calculate several measures of effect, the risk ratio, the risk difference, the odds ratio, and the incidence rate ratio, how to interpret these measures of effect, how different methods of selecting controls affects the odds ratio, and the basics of two different methods of analyzing survival, Kaplan-Meier curves and hazard ratios. In our last podcast, we discussed exposure and outcome and how to study whether an exposure caused an outcome. Now we want to know whether X caused Y and how to quantify that effect. We'll start by calculating the risk, the most common and most intuitive measure of disease occurrence for each of our study groups. Let A represent the number of persons who develop disease over the study period, and N represent the total number of persons being followed. The risk is A over N. Note that A is likely to change depending on how long subjects are followed. Therefore, when discussing risk, a period of time must be specified. To know whether X causes Y, we calculate the effect of the exposure by comparing the risk in our exposed and unexposed groups using the risk ratio, or the risk difference. If X has no effect on Y, then the risk in the exposed will be the same as the risk in the unexposed. To find the risk ratio, divide the risk in the exposed group by the risk in the unexposed group. The result is the increase in risk of the outcome that is attributable to the exposure. To find the risk difference, subtract the risk in the unexposed group from the risk in the exposed group. The risk difference is often used to quantify the effect on a population level. Let's do an example. In this 2x2 table, the columns represent the exposed and unexposed groups. We put the totals at the bottom. The rows show the disease outcome for each group, the number of diseased on the top row, and the number of non-diseased in the bottom row. Let's say we have an 8-week trial of 20,000 subjects. 10,000 patients have taken aspirin and 10,000 have not. Of the exposed, 400 develop a GI bleed. Of the unexposed, 100 do. We don't need the C and D cells to find the risk ratio, but we'll fill them in now for completeness. The risk among aspirin users is A over the total number of exposed, or 400 over 10,000, which equals 0.04. The risk among non-users is B over the total number of unexposed, or 100 over 10,000, which equals 0.01. The risk ratio is 0.04 divided by 0.01, which equals 4. Subjects in our exposed group are 4 times more likely to have a GI bleed than in the unexposed. The risk difference is 0.04 minus 0.01, which equals 0.03. This means that stopping all aspirin use would prevent about 3 cases of GI bleeding for every 100 people. What if this was a study of Reye's syndrome and only 4 persons exposed to aspirin developed Reye's, while only 1 person in the non-aspirin group did? Our risk ratio is still 4, but our risk difference is now only 0.04% minus 0.01%, which equals 0.03%. Stopping all aspirin use would only prevent 3 cases out of every 10,000 persons, rather than the 3 out of 100 persons with GI bleeding. The population level effect is much less impressive. A public health agency might be much less willing to spend money on a campaign warning people about the risks of Reye's syndrome than they would one about GI bleeding. The risk ratio and the risk difference only apply to cohort studies. With a case control study, we cannot use a risk ratio. We have to use the odds ratio. To better understand odds, let's take an example from gambling. When you roll a single die, the chance of rolling a 6 would be 1 in 6, because there are 6 possible sides, only one of which is a 6. To find the odds of rolling a 6, however, you take the chance of rolling a 6 and divide it by the chance of not rolling a 6. 1 over 6 divided by 5 over 6 equals 1 over 5. Like we did with risk, we can calculate the odds ratio. The odds of disease in the exposed divided by the odds of disease in the unexposed. The odds ratio is much less intuitive than the risk ratio, but under the right circumstances, the odds ratio is a good approximation for the risk ratio, which we tend to have a better feeling for. The relationship between the risk ratio and odds ratio can be shown in the following example. Let's look at a cohort study first. We have 500 persons exposed to aspirin and 500 unexposed. Here, 400 persons in the exposed group developed a GI bleed, and 100 persons in the unexposed group did. The risk ratio is 4. Now we'll see what happens in a case control study. We start by finding a total of 500 cases. Next, we find controls by sampling persons in the cohort who are not cases. We analyze the data and find that of the cases, 400 were exposed and 100 were not. Of our controls, 200 were exposed and 300 were not. The odds ratio will be 400 over 200 divided by 100 over 300. This equals 6. The major point here is that the odds ratio tends to exaggerate what would be the corresponding risk ratio in a cohort study. This means that odds ratios above 1 will be larger than the corresponding risk ratios, and that odds ratios less than 1 will be smaller than the corresponding risk ratios. Under some circumstances, the odds ratio can equal the risk ratio, but that's beyond what we can talk about here. The study designs we have looked at so far follow all subjects for the same fixed amount of time. Here's a study where this is not the case. To analyze these data, we can't simply count the number of people in the study to calculate risk, since they aren't all followed for the same amount of time. Instead, we need to account for the amount of time each subject is followed. To do this, we use person time. This subject, who stays in the study for 2 months, contributes 2 months of person time. This one, 12 months of person time. The sum of all person time for each subject gives us the total time in which events could have occurred. The number of events over the person time gives us the incidence rate. Note that incidence rates are always expressed as fractions, with the number of events in the numerator and the unit of person time in the denominator. The incidence rate is used to calculate the incidence rate ratio and the incidence rate difference, which is interpreted and used in much the same way as the risk ratio. Another measure to look out for with this type of study is the hazard ratio. The hazard ratio is the result we get when using a Cox proportional hazard regression model, which we won't go into here. It is interpreted the same way as the risk and rate ratios. Be aware that each of the ratios we have discussed can be referred to as a relative risk, and you will find this term used for each of them as you read papers. Also confusingly, the relative risk is abbreviated RR, like the risk ratio. It's up to you to decide which measure the authors really are referring to. Finally, let's talk briefly about the Kaplan-Meier plot, which is used in time-to-event analyses, but is not a measure of effect. It is also known as a survival analysis. A Kaplan-Meier plot shows time on the x-axis and survival on the y-axis. A line represents survival in each group, allowing us to visually compare them. When the line falls, a subject has had the outcome. Where there is a tick mark, a subject has left the study for other reasons. This subject is no longer contributing person time. Because they have not died or had an event, the line does not fall. This subject is therefore said to be censored. There are 3 pieces of information that we get from a Kaplan-Meier plot. First, whether the exposure group has a statistically significant probability of the outcome than the unexposed group. This is given by the p-value associated with the plot. Second, we can determine median survival, which is the median amount of time people are free from the outcome. It's determined by drawing a line from the 50% mark on the y-axis across to where the line crosses the data plot. Dropping a line down from there to the x-axis gives us the median survival. If the line from the 50% mark doesn't hit the data plot at all, then we can only say that the median survival was longer than the study duration. Third, we can determine the probability of survival at a certain period of time. This is determined by drawing a line up from the x-axis at the time point we're interested in, say 6 months, and reading from the y-axis the probability of survival. This is also the probability of being free of the outcome. Now let's look at some papers. Let's first look at the paper by Solomon and colleagues concerning cardiovascular risk in COXIB and traditional NSAID users. We'll focus on Table 3. This table has a lot of information, but let's focus on 2 lines. The top one showing events in celecoxib users, and the bottom one showing events in non-users of any kind of NSAID. We saw before that this is a cohort study where subjects are followed over time and classified as exposed or unexposed by whether they start using an NSAID or another unrelated drug. Therefore, we're going to use these data to calculate risk ratios and incidence rate ratios. For a second, let's pretend that time is not a factor in this study and that all subjects were followed for exactly the same length of time. Therefore, the column labeled N gives us the number of subjects in each exposure group: 26,366 celecoxib users and 23,532 non-users. And the column labeled Events gives us the number of cardiovascular events in each exposure group: 1,342 in celecoxib users and 1,847 in the non-users. Therefore, the risk among celecoxib users is 1,342 over 26,366 equals 0.0509. And the risk among non-users is 1847 divided by 23,532 equals 0.0723. The risk ratio is therefore 0.0509 over 0.023, which is equal to 0.7. The risk difference is 0.0509 minus 0.0723 equals negative 0.0214. These both suggest that use of celecoxib protects users from cardiovascular disease. Users had 0.7 times the risk of a cardiovascular event as did non-users. We can use the risk difference to calculate a number needed to treat, which is 1 over 0.0214, which equals 46.7, suggesting that for every 47 persons that we treat with celecoxib, we will prevent 1 cardiovascular event. If you're paying attention, you know that these values cannot be correct. We know that celecoxib is not protective in cardiovascular disease and in fact elevates the risk slightly. These values are biased by the fact that the subjects were not followed for a uniform period of time. Risks and risk ratios were not the correct measures of effect. We need to incorporate time. The fourth column shows the total amount of person time for each exposure group. For celecoxib users, this is 11,768 person years. For non-users, 16,067 person years. The incidence rate of cardiovascular events for celecoxib users is 1,342 over 11,768 person years. This equals 0.114 events per person years, or 11.4 events per 100 person years, which is the value given in the column labeled incidence rate. The incidence rate in non-users is 1,847 over 16,067 person years, which equals 0.108 events per person year, or 10.8 events per 100 person years. The incidence rate ratio is therefore 11.4 over 10.8, which equals 1.05, which is the unadjusted rate ratio given in the final column. The incidence rate difference is 11.4 over 100 person years minus 10.8 over 100 person years equals 0.58 per 100 person years. Note that the denominator should have been included in the column label. Now we see that celecoxib use is associated with a small increase in the risk of cardiovascular events. Also note that the incidence rate difference cannot be used to calculate a number needed to treat or a number needed to harm. You need a risk difference for that. All the remaining numbers in this table can be calculated in the same way, giving an assessment of the risk of using the drug compared to no use.